So, hi everyone. In this talk, I will discuss about one of our recent work based on Scalaron as a dark matter candidate. So, as we all know that there is no universally accepted origin for the explanation for the uh, origin of cooled dark matter, and there have been extensive experimental search for particle dark matter ca- candidates, and still now there is no significant and uh, uh, conclusive evidence for such candidates. So, this suggests that if there is an interaction of dark matter with the standard model, then it is very feeble. And the natural question arises in this context is that is there any mechanism within the existing setup so that we can explain the observed dark matter relic density. Now, we know that all particles interact with each other through gravity. So, if dark matter comes from the gravitational sector, then there will be a natural suppression of interaction with the standard model particles, and this will naturally lead to the non-observation of these signals in the direct and indirect experiments. So, in this work we have considered the r square gravity, and we want to see if this r square gravity can account for the origin of dark matter. Okay. I will start with this action. So, in this action we can see, so this is the Einstein-Hilbert term, and we have incorporated the r square correction, and this term has been extensively used in the context of inflation, which was originally introduced by Starobinsky, but in this work we have used this term to see if this can account for the origin of dark matter, and this is the Lagrangian corresponding to the Higgs field. And we have also incorporated a non-minimal coupling of the Higgs field with curvature. These kinds of terms are very well studied in the context of Higgs inflation. Okay. So, now if we do a conformal transformation of this action, we can go over to the Einstein frame, and in the conformal factor is given by this, where this phi field, which is the scalar degree of freedom of r square gravity, is known as the Scalaron field, and after choosing an unique canonical unitary gauge, we will get this effective potential for this phi field in the Einstein frame. As we can see, there is an explicit interaction of the Higgs field and the phi field in the Einstein frame, besides that coming from the non-minimal coupling. Now, having this potential, we can write down the evolution equation for the Scalaron, and this is with the evolution equation, where we have assumed that this phi field is very smaller than the Planck scale. So, this is now the evolution equation where this phi 0 h. So, this is the minima of the effective potential. As we can see, this minima depends on the Higgs field. So, as the Higgs field, if the Higgs field has dynamics, then this minima will also shift. Now, let us consider a very specific condition, which is this condition. If this condition is satisfied, then this phi naught h is 0. So, the scalar field is effectively free, and we have this equation. Now, to produce dark matter in this context, we have to rely on the standard misalignment mechanism, which happens due to Hubble friction. So, when at a very early times when the Hubble friction is very large, phi is misaligned to some initial value, and then oscillation starts when the Hubble becomes comparable to the mass of the scalar field. And in that case, we can explain the observed relic density, and the relic density can be obtained using this formula for such a misalignment mechanism, and this comes out to be this one. So, now here the relic density depends on the non-minimal coupling and the initial misalignment of phi. Also, and by this relation, the mass also depends on the non-minimal coupling xi. So, if we fix xi and then demand that this relic density should match the observed relic density, then we will have bounds on this phi initial. So, this is the plot of the parameter space. So, in this axis we have the mass of the scalar field, and in this axis we have the initial misalignment. Both depends on the value of xi. So, xi is actually the independent parameter in this plot, and this is the line for the observed relic density. So this part is excluded by LHC constraint and this part are excluded by gamma ray. So these are very preliminary results that I want to mention. Now, so as you can see that if we assume that the scalaron constitutes whole of the dark matter, then still a range of mass is allowed where the phi initial is at around 10 to the power 10 giga electron volt and the mass like keV to meV masses are still allowed. Okay, so this is for the very specific condition. Now we will consider the case when we don't assume any condition. So in that case, the Higgs field has a dynamics and the minima of the Scalaron field is not equal to 0. So in that case, we can find the crossover temperature where the electroic crossover of the Higgs field happens. For that, we have to incorporate the thermal correction to the Higgs potential, and the crossover temperature comes out to be 154 giga electron volt. Okay. Now, before the electroic crossover, Higgs was sitting at H equal to 0, and therefore the initial value of the scalaron is given by this. So here we have a natural kind of misalignment without any fine tuning. So this is very novel in this context. So the dynamics of the Higgs field will now determine the misalignment and will determine the shift of this phi field. Now after the electroic crossover, this is how the Higgs field will evolve, and this will also lead to a dynamics of the scalar field. The minima of the scalar field will evolve using this equation, and as H attains its vacuum expectation value V, the minima will give will be 0 and the scalar field will oscillate around this minima at phi equal to 0. Okay. So now we can write, if we write this equation in terms of these dimensionless variables, we will have this equation for the scalaron evolution, and we need to solve this equation to see if the scalaron can account for the cold dark matter. Now using this entropy conservation and assuming a radiation dominated universe, we have obtained this solution for the scalaron field or the dimensionless field, and this is actually an oscillatory part, and this is the mean shift or the average shift of the minima field of the minima of the scalar field. Now using this approximate solution, one can show that that if we define this quantity chi, which is given by this, then this quantity I, which is a cube E, this E can be thought of an energy density of this chi field. This actually remains constant, and as H attains its wave value, so this becomes 1. So the chi field becomes the phi tilde field at late times. So E is the effective energy of phi tilde field at late times. So and now this quantity E always scales as matter, because we always have a 1 by a cube scaling. So we can find the scalar energy density at late times if we multiply this E at late times by the initial phi square, and the relic density comes out to be this, which is a function of m. If we demand the relic density to be 0.12, then the mass of the scalaron is fixed at of the order of 10 to the power minus 3 electron volt. So the mass comes out to be very small in this case. Now now we have used this mass value for the numerical computation, where we have incorporated the variation of G star and the full system, no approximation. So this is the evolution of the scalaron field, as you can see. So this dashed line is the minima shift of the scalaron field, and on top of that there are small oscillations. And this is the plot of the energy density of the scalaron field. This dashed line actually gives radiation like scaling, and this is the quantity phi I squared E, which scales as matter. As you can see, initially the scalaron field behaves as radiation, and after that there is a transition, and then it follows this quantity which scales as matter. So there is a radiation to matter like transition at some epoch, which means that with this mass, this field can explain the origin of cold dark matter. Okay, now these results can be readily extended to the case. All this case is for xi equal to 0, which is the simplest case. All the results can be extended to the case where the non-minimal coupling is not equal to 0. And in this case, if we again demand the relic density to be 0.12, the mass of the field comes out to be this. This is a transcendental equation. However, we can find the root of this, and as we can see, the mass doesn't change for the allowed range of xi. So even with the non-minimal coupling, the mass comes out to be of the order of 10 to the power minus 3 electron volt. and there is a transition from radiation to matter-like behavior far before matter-radiation equality, and no violation of BBN constraint. Okay, so I will summarize and conclude. What is the aim of this work? The aim of this work is to explore the potential of R-square gravity in explaining the origin of cold dark matter in the presence of a non-minimal Higgs coupling, and for that we have the mechanism is that the scalar degree of freedom of R-square gravity is producing the cold dark matter by two different misalignment mechanisms. In the first one, a very specific condition is needed, and we need to misalign through Hubble friction because effectively there is no interaction, and for that a range of mass and initial misaligned values are allowed for matching the relic density. However, in this case where there is no specific condition, the misalignment is due to the explicit coupling between Scalaron and Higgs, which is very novel because we don't need any fine-tuned condition. This is misalignment to coupling, and then there is a transition from radiation to CDM-like behavior, but the mass comes out to be very small. So these are all the results that I wanted to discuss, and these are the references which I have used to prepare my talk. And I want to thank ANRF for the financial support, and thank you for your attention.